Okay, so welcome to my channel Maths Corner, and we are live. And today we are here with yet another topic, that is Fermat Little Theorem. And my name is Savan Biklia. So if you have not subscribed my channel Maths Corner, so hit the bell icon and subscribe my channel. Okay, so we are now starting with Fermat Little Theorem today, and we will see the statement also, and we will see the proof of Fermat Little Theorem also. Okay, so let's start with the first of all the statement of Fermat Little theorem. Okay, so if we have that a raised to power p minus 1 is congruent to 1 modulo p. So before moving to Fermat theorem, you must have a good knowledge of modular arithmetic, a good knowledge of modular arithmetic, and some basic congruences you must know. Okay, some basic congruences you must know. So let us move to Fermat theorem. So if we have that a raised to power p minus 1 is congruent to 1 modulo p. That is, when a raised to power p minus 1 is divided by p, when a raised to power p minus 1 is divided by p, the remainder is going to be 1, provided that p is a prime number and the GCD of a comma p is 1. That is, there does not have any common factor between a and p. If this condition true, and we can say that the Fermat theorem can be applied here, and we can say that a raised to power p minus 1 is congruent to 1 modulo p. For example, let's take a is equals to 7, and let's take p is equals to 3. Okay, now as GCD of 7 comma 3 is 1, so I can apply Fermat theorem and write down that 7 raised to power 3 minus 1, which is 2, is congruent to 1 mod p, which is 3. So if I write down 7 square, which is 49, and which is 2, 49 when divided by 3, the remainder is coming out to be 1. So this is the Fermat theorem statement. Now, knowing the statement is not just enough. So let us move to the proof of this Fermat theorem. Okay. So this proof is there are various proof available. Some are with binomial, and some proof are with binomial coefficients, the binomial expansion. But this proof is something elegant. So let us move to that proof. But before moving to the proof, you must have a basic idea about the invertibility in number theory. Okay. So let us understand what is the invertibility in number theory. So we say that suppose we have a number a, and when you multiply this number a by another number b, and if we take this number modulo p, that is when we take the remainder when this is divided by p, it coming out to be 1. That is, ab is congruent to 1 modulo p. Then we can say that b is the inverse modulo p of a, or a is the inverse modulo p of b. But provided that here GCD of a comma p and should be equals to GCD of b comma p, and this both should be equals to 1. That is, a and b should be co-prime with p. A and b should be co-prime with p. And we also write that a is inverse modulo p of a, and b is inverse modulo p of b a. So we can say like this. That is, a is inverse modulo p of p. We can say that a is congruent to we can say that A is congruent to B inverse modulo P. And or we can also say that B is congruent to A inverse modulo P. Okay. Okay. So this is the basic concept of invertibility in number theory. Now we will use this concept to we will use this concept to prove the Fermat Little theorem. But let us see an example. Let us see an example. Suppose when we divide any number by a prime number, let's say the prime number is 7. So reminders, what can be the reminders? Okay, so when any number is divided by 7, the remainder can be 0, 1, 2, 3, 4, 5, or 6. So this can be the reminders when any number is divided by 7. Okay, so the if we take any number here, if we take the any number from this set and try to find it inverse modulo 7, because this is the set of reminders when a number is divided by 7. This is the set of reminders when a number is divided by 7. We can denote this set by R7. Okay. So if we take 3, let for example, let we take 3. If we want to find out the inverse modulo 7 of 3, that is 3 into what number from this set is congruent to 1 modulo p. 3 into what number from this set is 1 modulo p. So let us take some hit and try. Okay, so if I take a 1, then I get 3. If I get 2, now here p is my 7. So I can remove p and write down 7 here. Okay, so let us substitute all the values and see that after which values the 3 into that number is coming out to be 1 modulo 7. So if I take 15, 3 into 5. Okay, if I take 3 into 5, then what I will get is 3 into 5. This is 15. And 15 is absolutely congruent to 1 modulo 7 as 14 is divisible by 7. Okay, so I can say that 3 is inverse modulo 7 of 5. Okay, so I can say that 3 is inverse modulo 7. Inverse modulo 7 of 5. Or vice versa. That is 5 is also inverse modulo 7 of 3. So I can see that none other numbers will inverse it with this thing. Okay, so the inverse of 3, the inverse of 3 is unique. That is not the other number can be exist with the inverse of 3. That is the inverse of 3 is only 5. If we take another number, then it can't be the inverse of 3. So the this claim I am doing it my claim is that the inverse of any number in certain modulo prime number is a unique and it always exists. But the thing that I want to tell you is some basic thing, that is the inverse of 0. The first thing that I want to tell you is that the inverse of 0 never exists, because 0 into any number is always congruent to 0 modulo of prime number. 0 modulo of prime number. So we can't get 1 as my residue when any number is multiplied with 0. You can always get the remainder 0 only. So I can say that the inverse of 0 does not exist. And also, if I take the inverse of 1, the inverse of 1 is 1 only, because whereas the inverse is unique and the inverse of 1 is 1 only. And also the last number, that is 6. If I take 6, then 6 is congruent to negative 1 modulo 7. So if I multiply negative 1 with negative 1, that is 6 with 6, and I will get 1 modulo p. So the inverse of 6 is also 6 only. So the things that I get is the inverse of 0 does not exist, the inverse of 1 is 1 only, and the inverse of 6 is 6 only. So these are the three things that I get, and all the other, there are, as they are left with four numbers. We are left with four numbers. It is 2, 3, 4, 5. Then here we have 3 is a inverse of 5 and 2 is a inverse of 4. Okay, because 4 into 2, 8 is congruent to 1 modulo 7. So we can say that the inverse of any the inverse of any number is unique and it always exists irrespective of 0. Okay, so 0 can't be counted. So we can remove the 0 from this set. We can remove the 0 from this set. Okay, so let us take an examples first. First of all, we have said that the inverse of any number exists and is always unique. But this is true for we have this proof for only the prime number 7 case. But we want to prove it for all the cases. So I am making a claim. So let us make a claim. I am making a claim that I have the GCD of a comma p is 1. I am taking an a to be an arbitrary number. It is if the GCD of a comma p is 1. Okay, so then I define a set. Then I define a set which is set S. Let us define a set S. Then the set S is the set of reminders when any number is divided by p. Here p is a prime number. P is a prime number. So I am defining a set S where the set S is a set of all reminders when a number is divided by p. That is, I am not taking a 0 because the inverse of 0 doesn't exist. So this is 1, 2, 3 till p minus 1, because this is a set of the reminders when any number is divided by p. Okay. Now, if I take any two numbers from this set, if I take any two number from this set, a comma b, a, let's say a, if I take any number a from this set, then there exists an another number b, where b belonging to set S. such A comma B belonging to set S such that AB is congruent to 1 modulo P. Okay. So if I take a number A from the set S, then there always exists a number B such that AB is congruent to 1 modulo P, or we can say that there always exists the inverse of A in the set S only. Okay. So there always exists the inverse of A in the set S only. So what can I say about this? So how can I say that the inverse is always unique and the inverse always exists? Okay. So first of all, I am making another claim. I am making another claim that none of the numbers, all the numbers is divisible by p, or I can say some of the numbers in the set S is divisible by p. Okay, so I am creating a new set. Let us create a new set that is AS. So AS, I am creating a new set. Now the set AS is the set in which all the element of S are being multiplied with A. Okay, so my set AS will be 1 into A, which is my A, 2 into A, 2A, 3 into A, 3A, and so on, 3A till P minus 1 times A. So I've done nothing, I have just multiplied every element of S with A, where I assume the GCD of A comma P is 1. Okay, so let us give another name to the element of AS, that is, I am calling A as A1, 2A as A2, 3A as A3, and so on till A P minus 1 as P minus 1 into A as A P minus 1, like this. Okay. Now, first of all, I'm making a claim that there exists a number AI, that there exists a number AI from the set AS only. So, if this AI is there in the set AS, then I can say that the 1 is less than equals to I is less than equals to P minus 1. Okay. Suppose I am making a claim that this AI is divisible by P. So what is my AI? My A1 is 1 into A2 is 2 into A3 is 3 into A. So my AI will be I into A, I into A. Okay. So my claim is that P is this number is divisible by P. So let's say if this is number is divisible by P, then I can say that P divides this number. P divides I into A. Now when a prime number divides I and A, so can I say that either P divides I or P divides A, or both can be true, but if this so, then both can be true also. So if a P divides A into I, then can I say that P divides I or P divides A? Now clearly we can say that P does not divide I, because I is less than or equals to P minus 1. So I is less than P, so how can P divides I? How can a bigger number divides a smaller number? So this is wrong thing. Now second is P can divides A, but P can't divide A because I am assumed that GCD of A comma P is 1 in my starting only. So I can't say that P divides A. So this is a contradiction. This is a contradiction. So I can say that none of these numbers, none of the AI are divisible by P. So I can say that A, 2A, 3A till P minus 1 into A. This all numbers will give some reminders when divided by P. Okay. So my AI, I am assuming can I assume that my AI will be P times Qi, my AI will be P times Qi plus some reminders Ri, some reminder Ri. The quotient will be same because this all numbers are less than P. So the quotient will be same. So AI can I assume as P Qi plus Ri. Now if I want to prove that all numbers will give different reminders, because there can be some numbers which can give the same reminders, but I don't want that number. So let us assume that there exists two number, let's say AI and AJ, AI and AJ, such that they both give same reminders upon dividing by P. That is, AI is congruent to AJ mod P, AJ mod P. Suppose they are giving the same reminders upon dividing by P. So my what is my AI? My AI is A into I, A into I, and this is A into J. So can I transfer that on my LHS and get a into I minus j. This thing is congruent to 0 modulo p. Okay, this thing is congruent to 0 modulo p. Now clearly this a does not divides p, that is GCD of a comma p is 1. So can I say that I minus j is congruent to 0 modulo p? This implies that I minus j is congruent to 0 modulo p. Okay, but I have from this I can say that I is congruent to j modulo p. But this can't happen. This can only happen when I is equals to j, because I comma j is less than p minus 1. Okay, so there can't be some have a difference greater than p. So I can say that I is congruent to j modulo p is only possible when I is equals to j. So only the same numbers I is equals to j. That is, if ai is equals to aj, then only I can say that they will both give same reminders. So this can be said that this can say that all AIs are giving different reminders. Okay, so all AIs are giving different reminders upon dividing by the prime number p. Upon dividing by the prime number p. Okay, so AI is equals to AJ if and only if that I is congruent to J modulo p, or vice versa can be true also. So I can say that all AI, that is A, 2A, 3A till P minus 1 times A, all will give the different reminders upon dividing by A. But that reminders will be from set S only. Because upon dividing by P, the reminders can be 1, either 2, either 3, or P minus 1. So what I can say is, my A1 is I can say A1 is my A only. So this A, 2A, 3A, 4A till P minus 1 in times A. This all will give different reminders which I have proved before. Okay. So 1 into A, that is A will be congruent to something reminder modulo P. My 2A will be congruent to something modulo P. Okay. And so on, so on, so on till my P minus 1 into A will be congruent to something modulo P. But this something is always different in each case. Okay, so this is always different in each case, and it will belonging to the set that my 1 2 3 till p minus 1. Okay, so this all something will be from this set only. And when I multiplied all these congruences, as the modulo p is same in both on both sides. Okay, so what I will get on my LHS, my LHS I will get 1 into 2 into 3 till p minus 1, which is my p minus 1 factorial. P minus 1 factorial into a raised to power. How much time the a is coming? 1, 2 till p minus 1. That is a raised to power p minus 1. Okay. This thing will be congruent to this reminders, the multiplication of the all the reminders. But as the reminders are all different, so none of the reminders will repeat. And there are p minus 1 reminders. So as all reminders are different, and the reminders can come from this set only. And in this set also, p minus 1 reminders are present. So I can say that all these reminders will be multiplied together. So there's 1 into 2 into 3 till p minus 1, which will comes out to be p minus 1 factorial. Okay, modulo p. Now I am reaching towards I may end. So I can cancel this p minus 1 factorial if and only if the GCD of p minus 1 factorial and p is 1. Okay, so what I have get, I can write down here. It is my p minus 1 factorial I have got into a raised to power p minus 1 is congruent to p minus 1 factorial modulo p minus 1 factorial modulo p. Now if my GCD of p minus 1 factorial comma p is 1, that is, what is my GCD? What is my GCD of p minus 1 factorial comma 1? P minus 1 factorial comma p. Now as p is a prime number, so p minus 1 factorial is 1 into 2 into 3 into 4 till p minus 1. That is 1 into 2 into 3 into 4 till into p minus 1. Now, as every number less than p, less than a prime number p, is not divisible by p. Okay, for example, let's say 7. None of the number that is 1, 2, 3 till 6 is divisible by p, because these are less numbers. And if I multiply to all numbers, so this so no number in this set will give 0 modulo p. So the multiplication will not never give 0 modulo p. So can I say that there's a GCD of p minus 1 factorial comma p for p is equals to prime, for p prime this is equals to 1. So if this is the GCD of this thing and this thing is 1, so can I cancel out this factor from the both side? So can I cancel out p minus 1 factorial and p minus 1 factorial? So here 1 will be left, and this is the proof of my Fermat theorem. We are left with 1 on my RHS and a raised to power p minus 1 on my LHS. So I get that a raised to power p minus 1 is congruent to 1 modulo p. Okay, so this is my Fermat theorem. So this was a total elegant proof of the Fermat Little theorem. So I can also multiply a on both sides as GCD of a comma p is 1. So I can also multiply a, and this is a raised to power p is congruent to a modulo p. Now this is my Fermat theorem. It is just a game of name. It is my Fermat Little theorem FLT, and this is my Fermat theorem just FT. Okay, so this both are same only, but this is the proof. The proof is more important. It is a raised to power p minus 1 is congruent to 1 modulo p. This I have proved using some contradiction, some assumption, some claiming, and then some basic sense of reminders. I have proved this thing, and the main concept that is being utilized here is the invertibility. It is invertibility number theory. So using this concept of invertibility, we can also prove the Wilson theorem very easily. That I will bring the next video of Wilson theorem, and we can prove that also very easily using the invertibility. And this is the prerequisite of that Wilson theorem. Okay, so this is the proof of my Fermat theorem. So this much only for today. Okay, so thanks for watching my video. And if you have not liked my video, please like, subscribe, and share. Thanks.